Okay, hello and welcome to Baobab Soluciones YouTube channel. Welcome to our webinar on supply chain management and prescriptive analytics, which we conduct in cooperation with our partner AIMS. My name is Julio Lema and I am part of the Baobab team. With me here today is Dr. Alvaro Garcia, founding partner at Baobab, and he will be conducting this webinar today. For those of you in the audience, or those of you that will listen to this later, who do not know Baobab, let me just say that we are a boutique consulting firm based in Madrid, Spain, specialized in advanced analytics, prescriptive analytics, and operations research. And we are one of AIM's local partners here in Spain. And without any further ado, I give you Dr. Alvaro Garcia. Alvaro, the floor is yours.
Thank you very much, Julio, and thank you all for attending this webinar. And thanks for your interest in this topic, which is supply chain management and how prescriptive analytics can assist everything related to supply chain. I will first start presenting what supply chain management is, what decisions are relevant in this context, and I will explain how prescriptive analytics can assist the whole process. And then we'll move to a case study where we will use SC Navigator, which is a name-based tool. And finally, we will have some time for questions and answers. So let me borrow this slide we use for presenting ourselves, because I'd like to share a few words about who we are and what we do. I am a professor at the Technical University of Madrid, and I've devoted my whole career to operations research or prescriptive analytics, both teaching and researching. And 8 years ago, more than 8 years ago now, we founded Baobab Soluciones with a very, very clear mission, which was and still is to assist companies in making better decisions by using advanced mathematics, and that having a results on their results and having had dollar savings in their application of research, operation research. We are a privately owned company. We are located in Madrid, and most of our employees are engineers and mathematicians, and actually some of them hold a PhD. So back to our topic, let me use this definition by Simchi Levy, which is one of the gurus in supply chain. And although the definition is from 2000, it totally applies and is a very useful one to describe what this topic is. Let me just say that supply chain management is this set of approaches utilized to efficiently integrate suppliers, manufacturers, warehouses, and stores with the objective of having the merchandise produced and distributed at the right quantities, to the right locations, and at the right time. And we want to have all this done, minimizing system-wide costs and not forgetting about service level, which should be satisfied. So there are two relevant things here. We need to take into account the whole system, all the way from suppliers to stores. And in that sense, we want to take into account costs. There are multiple trade-offs in this context. So we want to have them into account and making sure that what we have in our supply chain takes into account and minimizes the total cost, and not forgetting about service level, because the customer is at the very end, and that gives sense to our activities. So in the area of supply chain management, we have, as in many other areas, we have decisions at different levels. At the very top, we have strategic decisions, and some of those are outsourcing, what we do in-house and what we outsource. The network design problem, which is the one that we will cover in the case study. We also have to decide where to produce what, and we also have to decide what our information systems are. These decisions are very important in unitary terms. So every time we make one of these decisions, there's a lot of money involved. They're not reversible, at least not easily reversible, and they have a huge impact in a long time, for a long time. At the very opposite to those kind of decisions are the operational ones, which are made very frequently And there's not much money involved. They are far more irreversible, and they might be seen as less important, but they are as important as the strategic ones, because a bad decision repeated over time might damage our results. Those decisions are production scheduling, decisions regarding buying, purchasing, inventory, our shipment schedule, and even the last mile delivery we have to perform on a daily basis. And somewhere in between, we have the tactical decisions. All these decisions are subject to apply prescriptive analytics, and we will see that in a minute. This context of supply chain management is a very complex one. So let me just give an example to illustrate that. So let's imagine one of the multiple supply chains we can think of, which is the airplane manufacturing industry. And for us to have an airplane, we have to start with lots of raw materials, from rivets, carbon fiber, steel, and many other materials we can think of. And for us to go all the way from the raw materials to the plane delivered to the airline company, which is the end customer, we have to arrange a supply chain like that of Airbus. This is an image that is available in their website, corresponding to the supply chain for the Airbus 320 family. And we can figure that this is a very complex network to coordinate and to operate. We have locations where we have manufacturing processes, we have transportation, and we have to coordinate that. This is even a simplified version, because in Spain we have more than one single factory, and we have to make all this work so that eventually all the sub-assemblies and assemblies are taken to, in this case, Toulouse, where there's a final assembly line and all the components are assembled. So all those decisions I mentioned before take place in this particular supply chain, in many others that you can imagine. So for us to address them in an efficient and effective way, we need powerful tools. And that's when prescriptive analytics come into the show. This pyramid here describes 3 layers of knowledge that correspond to different levels of value that we can obtain from different kinds of analytics. At the very bottom of the pyramid, we have descriptive analytics. This kind of approach allows us to make sense of large amounts of information. It allows us to display range information for us to make sense of what happens. So it provides value because it allows us to understand what happened in the past. It's something we do after things have happened. We can visualize, analyze correlations, and this is what we can think of as business intelligence in terms of descriptive analytics. We can go a step further, or a step higher in the pyramid, and we can use predictive analytics. This kind of analytics allows us to know what to expect in the future, to know how things will be. For example, we can forecast our demand, and actually we can even have an estimate of our demand depending on the prices we have. And this can allow us to prepare for the future. So we can foresee some scenarios and foresee what to expect depending on what we do. But we can go even further and go to the top of the pyramid, and that is prescriptive analytics, or what is called also operations research. And this consists on getting prescriptions, that's why the name is prescriptive analytics, and to get suggestions or prescriptions about what to do to get the best outcome according to some KPI. It consists in optimization, and this is where the money is. So this builds up from the previous layers because we need some predictive analytics. For example, if we know the demand, depending on the prices we're going to set for our products, we can have a prescriptive analytics tool that suggests what is the price for every single product we're selling. So this is the one we should aim for if we want to make the best out of our system. And we're going to use this approach in the context of supply chain management, and in particular in the network design problem in supply chain. So for you to clearly understand what prescriptive analytics is, let's see a very simple example that illustrates it. Let's imagine we are a manufacturing company and we produce bicycles, okay? And we produce two types of products, mountain bikes and racers. And we have different capacities. We can produce 20 mountain bikes per day or 30 races per day. And if we produced both, we have to do a setup, and we don't have the possibility to produce 50 bikes. So we lose some capacity, and we can only produce 40 bikes per day. Okay? And we have economic information about the revenue, the margin we get from our products, which is 50 euros per mountain bike and 45 per racer. So this is our problem, and this is the first thing we need to do to get information about what we want to get and what are the requirements of our system. And we translate that into mathematics, into model that we can treat formally and from which we can then get prescriptions. So what we want to get is the daily production of our system. And we translate that into variables. We won't get into the details of variables anymore along the webinar, but this is what we need to fully understand what is behind the scenes running in the tool we're going to show afterwards. So we have variables that are related to our decision. We want to know how many mountain bikes we'll produce daily. That is a variable which we call x of 1. And we want to know how many races we will produce in that very same day, and that we will call x of 2. And we need to fix, set what is the aim, what we want to improve or optimize. And in our case, that is our total margin, which is that expression there, which is a simple calculation, which is x1, which is the number of mountain bikes, times 50, and that gives us the total margin we get from selling and previously producing mountain bikes. And the same with the second term, which is x of 2 times 45. That is the money we make out of races. So if we sum those two values, we get the total amount of money we're making. And okay, we would like to be x of 1 and x of 2 as large as possible, because that means making money. But our system doesn't allow us to do that. That is where our requirements come into place, and we translate that into equations or inequations. In our case, this means limiting the values of x of 1 and x of 2, so that x of 1 cannot be larger than 30 and x of 2 cannot be larger than 20 according to the capacities we have. And the summation of both two variables cannot exceed 40. And finally, we impose that these two values are not negative. We cannot have antimatter or something like that, okay? So we have a formal description of our problem. This is our model, and now we want to get a solution out of it. So what we do is we can do this in a very simple manner, because we only have two variables. When we are dealing with more complex problems, we need to resort to more powerful tools like solvers that do all the math for us and give us the values for x of 1 and x of 2. In our case, we can draw very, very simply what we have to our left, and we have a straight line indicating that we cannot go above that value because we would be producing more than 20 races. The same for the mountain bikes. And there's a straight line we cannot cross, which is producing more than 40 bicycles as a whole. So we can identify a region of feasible solutions in orange in the slide, and we can locate all the possible production plans which correspond to feasible solutions in our problem. And we can efficiently explore where our optimal solution is. Okay, in our case, we can know that we have 30 mountain bikes and 10 races as the optimal solutions, and a revenue of close to 2,000 euros. So the good point about this is that we know for sure that there is no better solution than this. We can state that this is the optimal we can get. And we can also explore alternative situations. So, for example, we can explore what could happen if I had more capacity for producing both mountain bikes or races, or what if the price of the races were more than 45? Would we still want to produce 10 races, or would we like to produce more? And we can evaluate how the system will perform, or what is the best we can get out of our system if we change the conditions. So we can do this analysis beforehand, and then if it's worth it, we can implement that. And we will see that in our case study. This can be applied to a lot of situations in supply chain. It can be used for network design, as we will see in a minute. We can apply that to deliver our products and for composing our last mile delivery routes. We can use it as well for inventory management, so we can decide when to buy, how much to buy, what supplier to use. We can use it also to perform a layout design analysis. We need to redesign or build from scratch a new warehouse, for example. We can apply this kind of analytics beforehand and save lots of money and coming up with a good design. And we can use it as well for scheduling, to decide where to produce what and in what is the right sequence for our machines to operate in order for us to get the best outcome of our system. And finally, we can also use prescriptive analytics for pricing. As I explained before, we can have an estimate of our demand depending on the prices and have a prescriptive tool that gives us or suggests us the prices we can use for all our products, taking into account all the business and the technical requirements of the industry we are operating in. And in the rest of the presentation, we're going to focus on network design, which is a strategic decision to be made in supply chain management. And to introduce the topic, we simply can see that, okay, customers expect to find product at stores, but we have facilities that manufacture, but that typically, in most of our cases, cannot ship directly to stores because it's very costly. So what we can do is we can use intermediate distribution centers that can link stores and manufacturers. And this allows us to take advantage of transporting all our products in trucks and then having some kind of last mile delivery or delivering our products to supermarkets and customers go into the supermarkets to retrieve their products. But still, although this is the general approach, we have to make far more decisions. Imagine in this case, we have one factory up there to our right and 9 locations where we have demand. What we need to decide is how many warehouses we use, where do we locate them, and what capacity do they have, and how many layers do we use. For this very simple example, we could use this kind of structure, this kind of design, where we have one central warehouse and 2 regional ones and 2 layers, so that manufacturers send products to the central distribution center and then to local distribution centers and finally to end customers. Or alternatively, we could opt for a network like the one to our right. So the more facilities we build, the larger the fixed cost, but the lower will be our transportation cost. So there's a trade-off. We have to identify and we need to decide with this the design that will allow us to operate at the lowest cost in the future. The traditional approach for this kind of problem has been based mainly on very basic rules, which in the best case is using a spreadsheet, performing some calculations to analyze just a few alternatives. And this is a very slow process because for us to analyze an alternative, it takes quite a few time. And we end up just analyzing some alternatives with no in-depth what-if analysis. And that means committing to a poor design and eventually to high costs and low service level, which is something we don't like. The alternative is using prescriptive analytics, and the process performs as follows. Typically, we have decision makers that have requirements, preference, and identify the scope of the problem they want to address. And we have system requirements. So the Baobab experts or our analysts come into place and they understand and gather all the information relevant, both related to decision makers and to system requirements. And what we do is we build a model. This is the last time we'll have a variable in the webinar, and we have XOL, which is at the very core of these kind of models, which indicates whether we have to open a distribution center at location L or not. And we build in the equations, we build the objective function as we did in the simple example, but we do that to represent in a valid manner what our problem in our system is. In our case, our future network or the current network to be redesigned. After that, we build a computer model, and we need to translate that into something that it can be solved in a computer, and we feed that with valid data corresponding to demand, costs, capacities, and so on. And with that, we can explore the solutions effectively using the software in the computer model, in our computer, and we get a network design. The good thing about this is that we can talk to the decision makers and get their insights about this solution and include their preferences, as we will do in the case study, to obtain alternative network designs. And with that, and with in iteration, several iterations, we can end up with an eventual design that satisfies the decision makers' preferences. So let's move to the case study, where we want to redesign and explore what we can do with the supply chain. In this case, we're in the mere supply chain of a company that distributes 3 types of food products. We have ambient, cold chain, and frozen. And these 3 products require different temperatures and different transportation and different storage. And we have 31 distribution centers. 2 of them operate as central distribution centers and 29 as local distribution centers. For each of those, we know the fixed cost, which is the cost we pay just for having them operating, the throughput capacity, which is the maximum flow we can have flowing through each distribution center, and we have a throughput cost, which is the money we have to pay, or the cost we have for having an item of each of those products flowing through that distribution center. We have 269 demand locations. So for each of these locations and for every product, we know how much we're going to need to deliver, because that is our demand. And we have 6 suppliers, which have different capacities and different supply costs for every kind of product. So we buy products from the suppliers and deliver them all to our demand locations using the distribution centers I mentioned before. And we have transportation. We have 3 levels. We have primary transportation that goes from the supplier to the central distribution center. We have inter-resource, which is in between a distribution center, which is one of the central ones, to a local distribution center. And finally, we have the secondary transportation, which is that going from the local distribution center to the end customers. And we have a cost per unit and distance. So here we have a more complex situation where we want to have a good solution in terms of the trade-off corresponding to the number of facilities we use. The more use, the larger the fixed price, but the lower will be our transportation costs. And that is the objective, or what we want to minimize, which is the total cost, which is a combination of the fixed and variable cost for distribution centers, the supply, which is the cost we assume for buying what we're going to deliver, and finally the transportation, all 3 types of transportation I mentioned before. And we want to minimize that. And for us to make a solution, we want to know what to open and close for regarding our distribution centers, which our flow should be in terms of transportation, and the drive time, how far close we will be to our customers. That gives us a hint, or at least the first approach to how good our service level will be. And we would like to have a cost breakdown of the total cost that we want to minimize. For you to have an idea of how the complexity of this problem, we need to just know that we have 4.8 times 10 to the power of 111 combinations, just when it comes to the decision of opening and closing distribution centers. If it took us 1 nanosecond to check and to do the calculations for every combination, it would take more than 1 or 10 to the power of 85 times the age of the universe. So this gives us a clear idea that this is not a very good approach. Like brute force is not a very good approach, and relying on the traditional approach will only allow us to explore very few a number of those combinations, and that might lead us to not very good results. So what we suggest is using prescriptive analytics, and this is where we're going to use progress developed by ACME. ACME is a company based in the Netherlands that has been assisting companies in making good decisions by means of providing them with a very powerful platform to develop optimization models. And they have ACME, which is both the name of the company and the product that, as I said, is a general tool for you to develop in a very efficient manner optimization tools in any kind of industry. And they recently developed a product which is based on that platform for managing the supply chain, which has several applications. One of those is the Network Design Navigator, which is the one we're going to use. So let's move to the supply chain tool from ACME, SC Navigator. And I already loaded the configuration and the input data we're going to use. And this is what we would see if we had done that and expected for us to start working with the tool. So what we have here is a map with the locations for our suppliers in red, sorry, in blue, these dots here. We have the central distribution centers, okay, in Paris and Bucharest. And we have in yellow the different locations for the local distribution centers, okay? So first we're going to review the data we can access and that we can edit and change and play with. So first we're going to see the resource data. And we have information regarding every single distribution center. We have the fixed costs, whether they are available or not, and the capacity they have. We can also see the resource product data, which allows us to see the variable throughput costs. So some of the warehouses are more efficient and the throughput cost is lower and others are less efficient. We can also see the information regarding the demand. And we have a very large table where we have, for every location and every product, the number in items that we have as a demand that we need to satisfy. So we have that Harlem, for example, requires this amount of items of ambient products. If we scroll down, we can see that, for example, we have Porto and cold chain. We have this demand, and so on for the rest of locations and products. And we also have information regarding suppliers, locations, and other elements that allows us to configure our model to analyze how our system will work. So let's go to this view here, which is the flows, to which we will come pretty often. And what we see here is the very same map we had and some other widgets for us to get the results of our analysis and to display information. Okay, we see the dots we had here, and we add customers. We see the whole amount of locations that are involved in our decision, in our supply chain. So the first thing we're going to do is to get a solution. And when I click here, what I'm doing is I'm solving the model we created. We fed SC Navigator with the relevant information, and now the solver is working behind the scenes to give us the better solution that we can get. And we'll see that it takes no time compared to the time it would take us to get results in a traditional approach. And the good thing is that we know that what we are getting is the best outcome we can get. Okay, so I'm going to load this case because we have the results for the base case scenario, which is the data as is right now. And what we have is a total cost of 107 million euros. And we can see how that cost divides into different elements. We have the fixed cost, we have the variable cost. We can enlarge this table to see it better. We have the supply, which is the amount of product we're buying, and different types of transportation and the total cost. Okay, We can also download and save this information as a CSV file and use it for our own analysis. And we can get the information regarding all locations and all transportations. Okay, it takes some time for it to load, but we'll see it in a minute. Okay, and we can zoom in and zoom out and see how things are. This allows us to have an overview of how things are, but we can get all the details about how the solution is if we go to all the information regarding to customers, distribution centers, cost, supplies, transportation, and so on. So let's go to distribution centers and see how things are. So what we get here is a chart with as many elements as distribution centers, and we have two bars for each of those. What we have is the capacity in green, this is the green bar, and a yellow or orange bar corresponding to the utilization or making of that distribution center. And we have a table down here with all the details. But if we just take a look at how things are related now to our warehouses, our distribution centers, what we see is that we have Ankara, Beirut, or Bucharest close to full usage. So let me just show here the results to see them in a single view. So there's a high level of utilization of these three warehouses. So we might ask ourselves, what if we had some extra capacity? So what we can do is overriding the capacity constraints to see if investing is worth it. So we go back to SC Navigator, and what we're going to do is to go to Analytics, and we get a view where we can change and tune how the model and the tool behaves. What we're going to do is to activate one of the options, which is the one we see here, relaxed capacity. Okay. And we enlarge that, and we can check relaxed DC capacity. This allows us to override that capacity constraints and allow having a larger throughput in warehouses than the one that it would be allowed if we met the capacity constraints. So we now optimize again. And what we expect is to get a better solution than the one we had before, because we are allowing the tool to explore more possibilities. And we expect that SC Navigator will choose to use to a fuller extent or even more than the maximum capacity those warehouses that might allow us to take advantage of their usage. So if we go to flows, we can get, as we did before, the total cost and how it is divided into several components. And later on, we will see what the usage of our warehouses is. So we see that the total cost, I'll enlarge it. We see that the total cost has been reduced like by 100, a little bit less than 100,000 euros. And we can compare that. I already got the image for the distribution centers. And what we see is that we are exceeding the capacity of those three warehouses that were close to full capacity. Okay, so we can evaluate if those savings are worth the investment that we would need to perform for us to get that improvement. It doesn't sound very promising because it's not much money, and we would have to increase the capacity of some distribution centers, and that might involve loads of money that might not pay for the savings we would get afterwards. Okay, so the next thing we might think of is, okay, we might see that we have some warehouses that are very or totally underutilized. There are some that are hardly utilized, but these two ones, Ljubljana and Bratislava, are not used at all. So we might again ask ourselves if we should close Bratislava and Ljubljana. So we are going back to SC Navigator and we are going to perform that analysis. So we're going to analytics, and we're going to uncheck this relax DC capacity. Okay, and we're going to force to use only 29 distribution centers. So when I'm typing here 29, I'm making the minimum and the maximum number equal to 29. And I'm going to say to SC Navigator that I want Bratislava, which is here, to remain closed in the solution I'm going to get. And down here, I'm going to force Ljubljana again as well to remain closed. So now we're going to optimize, and we're going to save some money in terms of fixed cost. And the analysis is whether it is worth it or not. So is it the saving we expect from closing those two distribution centers going to pay off? So we got the solution, so we can go again to flows. If we go to flows, we see now the cost we have. Now we have something close to €1 million reduction in costs. So that might be worth it. That is something far more interesting. And if we go to distribution centers, we can see now the chart, and we don't see those warehouses anymore. And the flow that was being taken care of by those two warehouses has been distributed to some other warehouses. So if we go back to our comparison, okay, what we have is we have reduced the cost, and compared to the original situation, we're saving close to 100%, which is close to €1 million, which could be something worth analyzing, because we are just closing to warehouses. Depends on all the considerations regarding closing those two warehouses. And we can see that we have reduced our fixed cost from these 157 to 147, which is €10 million. But this doesn't translate into savings because the transportation costs have increased. Okay, we've come to a situation where we are interested or might be interested in closing these two distribution centers. So the question is, why not letting the model decide for us what to do? And that is what we're going to do. So we're going to use the full potential of prescriptive analytics, and what we're going to do is to tell the model to do all the analysis for us. So we are not going to tell SC Navigator whether to close Ljubljana and Bratislava. Instead, we are going to give total freedom to SC Navigator to do whatever is best, and we're going to analytics, and we're going to let SC Navigator to go from 1 to, that's a high, totally beyond what we can do, but we're going to set the maximum number of DCs to 150, and we're going to ask for a network design. So we expect a better solution now, because we are allowing SC Navigator to close as many distribution centers and correspondingly save the corresponding fixed cost. We will have some increase in transportation in exchange for that, but the balance probably will be positive. And we have the results, so we go back to flows. And we'll see the cost here. And indeed, it's been reduced to almost €101 million. And we see that the fixed cost is less than 7 million, which is far less than we had at the very beginning, but we have an increase in the rest of the cost, but the overall result is worth implementing. So that means a close to 6% reduction in cost, and we can see all the scenarios we're analyzing. So let me remark here that we're doing this here at no cost, comfortably within our computer, in our office, and not running any risks. And we can evaluate a very large amount of scenarios and then implement the one that gives us the best results. And we're doing that in no time. So let's take a look at the solution to illustrate some of the analysis we can do. If we go up north of Europe, Okay, well, we see, for example, we have Stockholm here and Helsinki that are both, I can uncheck the local distribution center, and we see that, okay, we have demand both in Stockholm and Helsinki, and okay, we have both in both locations distribution centers, but we're not using them. Okay, there's no flow coming out of those, so we are not using them, which means having all this part of Europe with no warehouses close to these countries. So we might not like that solution, because that might mean that if any disruption occurs, we might be quite far away from these end customers here. So one of the good things about this kind of approaches in prescriptive analytics is that we can introduce some things that are not exactly what we were thinking of at the very beginning, and see the impact, and introduce considerations and see the economic impact in our solution. So what we're going to do is we're going to disease, and we're going to force Stockholm to remain open. So we scroll down here, and we're going to see what is the impact. There we go. Sorry, I want you just to see that I'm checking the remain open for Stockholm. Notice that in this chart here, Stockholm does not appear, and we're going to get a solution now. So we expect the solution to be a little bit worse than the one we had before, because we are imposing something that is not what SC Navigator gave us. So we're getting away from the optimal, but we want to see what is the impact, and eventually see what is the overcost we have to have in order for us to have a more resilient or reliable supply chain. Okay, now we see that when we see our distribution centers after the solution is displayed, we have all this capacity and we are only using part of it, but Stockholm is open. So we need to see now what our costs are. And we expect, as I said, a more costly solution, but we can analyze if it's worth it or not. So we are a little bit over 101 million euros, which is a little bit worse than what we had before. So if we have the full picture for all our comparison, we have this last scenario with Stockholm open, and we have an increase in our cost that is barely 1.2%, which might be interesting, paying that amount of money for making sure that no problems occur when supplying the upper part of Europe. So this is what the type of analysis we can do with SC Navigator and applying prescriptive analytics in terms of our network design. But one thing we've taken for granted in our case is the fact that we have already some eligible locations for us to use, whether because someone gave us those locations or because those are the locations we actually have for our network in our current situation. But it might happen that we want to explore some new locations, or that we want to operate in a new market when no locations are available yet. So that might be a case where we need to explore eligible locations for us to get the best combination of them all to let us operate at the lowest cost. And that is where SC Navigator provides us with a center of gravity, which is another application we can use for exploring these eligible solutions. I'm not going to show the tool because it might take us quite a few time, but I'm going to give you some screenshots and explain how it works. Imagine for a moment we are in a different industry, we're a different company, and we want to operate in the Spanish market. And we have identified some demand locations, and we know all these yellow dots correspond to locations where we have some demand, and we know the demand, we have some forecast of the demand for every single location. We also have some suppliers, which are represented by orange dots, and we know where they are located and their capacity to provide us with the products we want to deliver to our end customers. And we have some estimation of our costs, both fixed costs and transportation costs and supply costs. So we want to decide where good locations are for us to give those to network design of SC Navigator and eventually have our design for our network. So we would like to be close to where customers are, because that way our transportation costs are lower. And we want to be close to suppliers, because that way the transportation from suppliers would be cheaper as well. So there's a trade-off again. So what we can do is ask a center of gravity to provide us with different locations. And when we do that, there's math running behind the scenes, calculating or getting the best trade-off for us to locate our facilities. So we can ask center of gravity to give us the best ideal location in case that we wanted to have just a single location, a single facility. And what we will get is something, a point, which is in the center of Spain, no wonder, given how demand distributes in the whole country. And it will be somewhere up north of Madrid. We could also ask center of gravity to provide us with 2 locations in case we wanted to have 2 distribution centers, and we would get these 2 locations. And we would also ask for 3 and so on, and we could get different solutions. And for each of those solutions, we could get some breakdown of our costs regarding the transportation and the fixed costs. So if we do that, what we get is, I said before, ideal locations for our distribution centers. So that means that we get the coordinates of those locations, and we need eventually to get some actual locations, because we might get out of center of gravity to locate a warehouse somewhere in the middle of the city, which is not possible, but it gives us some preliminary idea of where to find for good, or where to identify good locations. So what we would do is to explore the area where we are suggested by center of gravity, and then eventually find a spot which we can rent or buy or whatever, and use it as our actual location that would be the input for SC Navigator, in particular for network design. So this is the first part, in case we're designing a network that feeds network design, is the whole process. Identifying ideal location, human intervention to identify which are the actual locations that will be used for network design, and eventually do the analysis we did before. So this is not everything regarding to network design. There are additional features we can include to set the strategy of your company. So far, we have assumed implicitly that we are dealing with a single period, but in most decisions, we have to act over a set of years, and we might consider several periods, typically years, over which we make decisions. We might open warehouses 2 years from now, 3 years from now, and so on, or we might close them if they are no longer needed. Another interesting feature is the fact that demand, supply, costs, for example, are not deterministic. We don't know the values for sure beforehand. So we might include in our tool some sort of probabilistic approach, some stochastic approach, defining some scenarios for these at least 3 elements and the probabilities for all of those, so that we get a robust, let's say, solution that takes into account all those possible scenarios. We can also go a step further, and we've worked with several warehouses and a capacity for each of those, but we could have a range of capacities for each of those warehouses. And we could ask the model to give us what is the capacity we should have at each stage in time, so that we increase our capacity as required, but we do that in a less costly possible manner. And we can also include service level indicators. For example, we mentioned that before. If we locate ourselves closer to our end customers, in case any disruption occurs, we could act more rapidly, and we will be able to provide a better service. Or, for example, if we have all our facilities working close to full capacity, any disruption that occurs will cause trouble to us, and we will not be able to deliver products at the right time to our customers. So we can devise some KPIs for us to get solutions that allows us to eventually provide a good service level to our customers. That is related to network design, but there's life beyond network design, because once we have a well-designed network, we need to plan it and to operate it in an effective manner. And there are problems related to network operation and planning in supply chain. To illustrate a few of them, we should have a good demand forecast for us to feed our models and to make better decisions. So we have a good estimate of our demand. We will be able to operate efficiently, prepare ourselves for future for our future periods in which we have to operate. We need to have a plan, typically an annual plan, where we decide what will we produce in every facility and how things will develop over the year, typically with using a rolling horizon. We also need to take care of the inventory management. We need to decide where to buy, when to buy, and how much to buy for us to have the supplies, the products we have to deliver to our final customers. And we can go all the way down to our transportation plan and compose full truckloads or less than truckloads and decide what trucks to use and when to ship products to our customers. And for all those problems and those situations, we can use prescriptive analytics, because there's a huge room for applying prescriptive analytics at all stages, as I said, at all decision levels in supply chain management. So I encourage you to adopt this kind of approach that allows us to have the better solution and to explore beforehand what you can change in your system and see what the results will be. And then when they are checked in your model, use them in your real system with no risk and knowing what you can expect. I hope this gives you an overall idea of how to use prescriptive analytics and their applications in this area, and you find this webinar useful. Thank you very much. Let me just suggest you subscribe to our blog, and you'll have the chance to follow all kinds of information related to both supply chain and prescriptive analytics, and not only other industries are also can benefit from this approach. So again, thank you very much, and I'm available for you to any questions that might be of your interest regarding the topic of the webinar. Julio, over to you.
Thank you very much, Alvaro, for the great conversation. There are no questions from our live audience yet. We have some viewers. If there is any question, please just write it on the chat and we will reply right away. Okay. It seems that there are no questions from our live audience. So, however, for those of you who are watching at a later time, no matter when, feel free to post your questions in the comments section and we'll post our reply. I mean, for your information, this video will remain public forever. Alternatively, you can also contact us on our website, which is featured on the video description, and we will be extremely happy to send you a reply by whatever means you choose. So last, thank you to our partners at ACME for letting us use SC Navigator and promoting this webinar. We hope you enjoyed it. Don't forget to subscribe to our channel on our blog for more webinars and material on prescriptive analytics. You will find information on this video description. And that's it. Have a nice day. Thank you very much.